Good morning, physics people. This is Mrs. Balbus here. Actually, it's probably not morning when you're watching this. It's probably afternoon, but it's morning for me. So, as you're watching this, I am probably up at George R. Brown with the robotics team. So, cheer us on. By the way, if you guys have an opportunity, you're welcome to come visit us. But let's get back to chapter 11, because I know this is so exciting. You can't wait to hear more about it. So let's get back to, let's review first of all what our objectives are. You guys should all by now have kind of figured out the analogy of the water. We've gone through that a couple of times. I'm going to just review it very quickly for you. So if I have a circuit with voltage and a resistor, this is my voltage and this is my resistor. The analogy in a water system is if I have my pump coming around to a water filter. So just as the pump here is analogous to the voltage, the pump pushes water through the circuit, through the pipes, so does the voltage from a voltage source, such as a battery, pushes the current through the circuit. So in this case, our current is going this way. And just as a water filter here provides resistance to the flow of the water, so this resistor, such as one of these that we looked at the other day, provides resistance to the current flowing through the circuit. Which, by the way, I wanted to show you something kind of fun. So if you remember the other day, we did this little experiment, right? And why did we say we got a lot of current flowing through here? Because there's not a lot of resistance in aluminum. Actually, it turns out that the resistance in aluminum is very tiny. I looked it up. It's something like 2.7 times 10 to the negative 8 ohms. So that's pretty small. So basically that says it has little to no resistance. Aluminum is oftentimes used as wire. So if we did this, of course it doesn't take very long before it begins to get warm, and I can feel the heat from the electrons flowing through. But what if I were to try the same thing with this? I don't know if you can read this. Let me get a little closer. Okay, these are the resistors we looked at the other day. This particular one is 470 kilo ohms. That means 470,000 ohms. So it's quite a bit more than the aluminum. So what would happen if I put these resistors across here? Let's try it and hope I don't start a fire. Okay, I'll just keep holding it. And as you might expect, I don't really feel anything. Why? Well, let's talk about that. I'll keep holding it. I actually have two resistors in here. Can you see that? I have one resistor here and one resistor there. And I said each of them were 470,000 kilo ohms. So, I'm still holding it, by the way. Coming back to one of our other points here, the equivalent resistance of resistors connected in series, in parallel, or in combination. I actually have two resistors in series here, right? So, I actually have a circuit that looks like this. I have my voltage, and I'm coming around and I have one resistor and another resistor, and this is 470,000 ohms, and this one is 470,000 ohms, and here's my voltage, which I need a magnifying glass to see what the voltage is. I'm going to go see. Pause 1 second. Okay, I'm back. I forgot I had this with my physics box because I need this to read Brock's handwriting. Okay, so what does it say? This says we are at, where's the voltage on this thing? Magnifying glass, it says 1.5 volts. Okay, so 1.5 volts right there. All right, so let's do a quick calculation. Now, what equation do I use for this? I'll give you a clue. There's only two equations, right? Ohm's law, voltage equals current times, that's pretty small. I'll just rewrite it here. There's only two equations. V equals IR, Ohm's law, voltage equals current times resistance. The other one is P equals VI, power equals voltage times current. So which one am I going to use in this case? Yep, whoever said V equals IR was correct. That's the one I'm going to use. Yes, I can hear you. Ha. Okay, so what is my resistance going to be? Remember, in this case, it's actually equivalent because I'm going to look for the I value coming right here. Okay? I don't want to erase these values yet, so I'm going to write it right here. So voltage equals IR. The first thing I have to do is find my R equivalent. I have two resistors in series, correct? The current goes first through one and then through the second one. So I have to add those two resistances together. So if you recall, coming back to the equation, which I think we discussed ad nauseum before, but I'll review it for you. It is right here on page 249. If you have resistors in series, you just add them together. Can you see that? It's kind of got a glare. And if you have resistances in parallel, you use this equation. So our resistors are in series, so we're going to add them. So our R equivalent is going to equal 470,000 plus 470,000. So I have 940,000 ohms. That's a lot. Okay, I'm going to have to erase these. Somebody remember it. Now I'll just write it over here. 2.7 times 10 to the negative 8 ohms. All right, continuing on with the calculation here. So let's calculate current. In order to do that, I need to do some simple algebra rearrangement. So I'm going to first, I equals V over R equivalent. What's my V? My V is the 1.5 volts that I read off my battery. And I'm going to divide that by 940,000 ohms. And I get a very small number. I got to pause because I got to go find my calculator. Okay, I'm back. Found my calculator. Okay, so according to my trusty calculator, the current in this case is 1.5957 e to the minus 6 amps. That's not much. That's pretty small. Now let's redo this, the same calculation, which what if instead of having these resistors up here, what if I had the aluminum foil? So the aluminum foil values, as we pointed out here, is very, very tiny. Actually, it's actually going to be smaller than this because this is actually an ohms per meter value. It's a unit length, so I would actually multiply this by the length. My length is very small, but for the sake of argument, we're just going to use this because it's already pretty small. Ah, that's actually a little better, isn't it? Dark for me, but better for you. Okay, we'll try that. All right, so now let's redo this same equation with what if I had replaced the resistors with this strip of aluminum instead? What would my current have been? Had the same voltage, 1.5 volts, but now what am I going to have for my resistance? 2.7 times 10 to the negative 8 ohms. Type this into my trusty calculator. 1.5 divided by 2.7 e to the negative 8th, and I end up with 5.555 e to the positive 7th. So let's write this out with the decimals instead. So I would go 6 decimal places to the left. So I would have 0, 0, 0, 1, 2, 3, 4, 5, 1, 5, 9, 5, 7, so on and so on. Let's double check. 1, 2, 3, 4, 5, 6. Okay, so that's how many amps I would have if I use those two resistors. Now what do I have if I'm using the aluminum foil? I'm going to take the E or the decimal place the other way, so I'd have It's 1, 2, 3, 4, 5, 6, 7. Okay, so look at the difference between the two. When I use the two resistors, I have some ridiculously tiny amount of current, so small that I certainly couldn't feel anything at all. Or on the other hand, if I use the aluminum foil, I have quite a bit going through there, and certainly enough that I could feel the temperature heat up very quickly. Okay, so we've done some of the simple circuit calculations. Then we're going to move on to some that are a little bit more complex. But don't get nervous about it. It's really just the same simple steps you've applied. You just apply the same thing over and over again. It's kind of like the whole analogy how do you eat an elephant. It sounds like you can't eat an elephant because it's too big, but you eat it just one bite at a time. We're going to do the same thing. Yeah, I know elephants don't taste very yummy, but anyway, so we're going to apply the same thing to this circuit. This looks kind of, I redrew it on my whiteboard, so let's move over here. So we have this circuit. It looks kind of complex, and you think, oh man, I have no idea how to do this. But you do, actually. We're just going to do it one step at a time. So the trick to these is to look at them in pieces. So first we're going to start with just this piece right here. If I look at just this piece, wow, that was really messy. I have two resistors, and they are in series. We've done that several times before, so how would I combine these into one? I would simply say that my R equivalent equals R3 plus R4. Okay? Instead of calling it R equivalent here, I'll call it R5 because I just want to get a new number. Okay? So what I can do now is I can rewrite that right part of the circuit as just having one resistor like this, which I'm going to say is R3 plus R4. Okay? Now my circuit looks like this. So what would be my next step? My next step is, well, I would look at it this way. I have two resistors in parallel now, right? So you know how to do that. You know that the equation is provided back here on page, right there, page 249, and that equivalent resistor is just R1 times R2 over R1 plus R2. Okay? So I would just go through and I would apply both of these into that equation. So then I would be able to simplify that down to, I'm kind of running out of whiteboard space here. So that part of the equation would now be down to this, a new R equivalent. We're going to redo this with numbers. Okay? So then my whole circuit would now look like this. It got really tiny. So now I have a resistor and a resistor in series. Once again, you can just add them together like we did up here. All right, so now let's go through and do these with actual numbers and see what we get. Step one, again, as we just discussed, I'm going to combine these two because they're in series, and it's just a simple matter of adding them. So the new equivalent is just going to simply be 10.7, but that's K, so don't forget. Let's go ahead and put the numbers there. It's going to be 10,700 ohms plus 870 ohms. So I'll have 0, 7, 5, 11,570 ohms. So I can now redraw that right part of the circuit like this. And this value right here is going to be 11,570 ohms. So let's draw the rest of it in here now. So that's 7.6K. And then across the top here, I have 3.3K. All right, so what's the next step? Again, I just look at just this side. I now have two resistors in parallel, and I know the equation for that is going to be these two multiplied divided by these two added. So what is that going to give me? I'm going to have 7, remember it's K, so I'm going to have 7,600 plus 11,570, oops, that was supposed to be times divided by 76,100 plus 11,570, and that equals, pause for a second while I type this into my calculator. And I get 4,586.96, 4,586.96, okay, ohms. All right, so now I'm running out of space. What I'm going to do now is I'm just going to redraw this as 1. So we combine these now into one equivalent. So I take this new value right here and put it right there. So it is 4,586.96 ohms. Okay? All right, one step left, and I will have reduced this all the way down to just one equivalent resistance. What's the last step? Well, these two are in series, right? So I simply add the two of them together. So my final resistance is going to be, don't forget that's a K, 3,300 plus this one, 4,586.96. So I get 6,887. So I can now reduce this all the way down to one circuit with a resistance of this ohms. So this is my voltage, that's my resistance, and there's the current. So what we have done is we have taken a fairly complicated circuit up here with a couple of different resistors in series and in parallel and broken it down into one imaginary circuit with just one equivalent resistance. Now, why do I do all this? What's the purpose, you may be asking? Well, ultimately, I want to know how much current is going through this circuit. And so by breaking it all the way down to this equivalent resistance, I can now apply Ohm's law and figure out what is the current required through this circuit. V equals IR is the equation I'm going to use. Do simple rearranging. I equals V over R. The V is, did they give us a voltage in this example? They did not, so we'll just make one up. We'll use our little AA battery of 1.5 volts, excuse me, divided by our resistance. Pull out the trusty calculator. I have 1.5 divided by 7,886.96, and I get 1.90187 times 10 to the negative fourth, or 1, 2, 3, 4. Right? 1, 2, 3, 4 amps. So that's pretty small. Not a lot of current flowing through there. Okay, let's move on to another example. Did anybody have any questions on that? Okay, I don't hear any questions, so I'll move on. If you have a question, just raise your hand, let me know. Of course, I can't see your hand, so I'm going to keep going. All right, which one should we do next? We did 11.6. 11.7, is it going to be any different? Let's talk about that one momentarily. You're going to apply the same methodology. We have a resistor here, coming around, resistor here, coming around, resistor here, with one in the middle right here. All right, so again, you're going to break this down into pieces. Just simple application of one of the two equations, resistance in series or parallel, blah. In this case, I start here. I have two resistors in parallel, so I'm going to combine them using that first equation, and those two would simplify down to just one when you apply the R1, R2 over R1 plus R2, right? So I would apply that to get this. So my circuit then would look like this. Well, now it gets really easy because you have three resistors and the current is flowing all the way through the circuit like this. So all three of those resistors are in series. So the last step is I would just take all three of these and add them together. I would just have R plus R plus R, that value, and that value. Add them all together, and then eventually you'd simplify it all down to one equivalent imaginary circuit that would just look like that, with this being your new value. Okay, so you apply the same steps. What you have to do is just be careful and look at your circuit, start at the rightmost side, and just break it down step by step. Okay, so now we're going to talk a little bit about this gentleman, Mr. Kirchhoff, and some of the laws that he came up with. We're going to talk through some of these in this section 11.3.5, Kirchhoff's laws. So far we've been talking about a simple circuit where we started with a voltage and we came through a resistance and back. And we've talked about how the current flowed like this. But what I have not discussed with you is what happens to the current when I add a branch on here. We talked about this a little bit. We talked about how the current is going to divide, and some's going to go down one path and some's going to go down the other. And how much is going to go down each path depends on the value of these resistances. So let's say, for example, that I have a resistance value here. I'm just going to pick simple numbers 1 and 2. That means this resistance is twice as much as this. So I have a amount of current coming down here. Let's just say my current is 6 amps. Let's do some simple math. I've got 6 amps total coming through this current. Once I reach this branch point, some is going to go down this resistor and some is going to go down this resistor. How much is going to go down each one? Well, intuitively you can kind of figure it out, but we'll apply Kirchhoff's law. Basically what Kirchhoff says is, I'm going to call this down here I2, this I3, and this coming into the whole thing, the total current I1. So common sense tells you that the total current through the whole circuit, which is I1, is going to equal the sum of I2 and I3. In other words, once I get to this branch, some of it's going to go down here and some of it's going to go down here, but the sum of these two still have to add up to what the total current was. They call this a node right at this point right here. So what they're saying is that every node the current is branching. Now let's go back to our water analogy. It makes sense. Imagine this is a pipe. You've got so many gallons of water flowing this way, and it reaches a branch in the pipe. Some of the water is going to flow this way, and some of it's going to go that way. Imagine that this was a very tiny pipe, like a small half-inch carbon or copper tubing, whereas this one was a 6-inch wide big old piece of PVC. Where's most of the water going to go? Oh, I did that the reverse. This is the big one because it has the least resistance. So this is a big pipe and this is a small one. Where's most of the water going to go? The path of least resistance. The current will be the same. Now once we get down here to this node, the reverse happens. I2 and I3 add back together again. So all these electrons that are marching down this path divide. Some go this way, some go this way, but once they get around the circuit back to this node, they all combine back onto the one path again. So once I get back to here, I'm back to having the total sum, all those electrons once again marching together up and around again until they get once again to this node where once again they divide. Some goes this way and some goes that way. So that's basically the first of Kirchhoff's law. It says that the sum of the currents at any node have to equal the total. So the sum of the two currents here, I2 and I3, equal the total I1. And likewise, I get back down here, I2 and I3 sum up to equal I1. So that's the first of Kirchhoff's law. Now the second of Kirchhoff's law discusses everything in terms of voltages. So let's back up a little bit here. I'm going to start with a simple circuit. So when I have a current flowing through a circuit, I start with a voltage source. So what we were using this morning was a AA battery, 1.5 volts. And that's providing the push to push the electrons through the circuit. Once it gets to this resistor basically pushes back. This resistor is resisting the flow and saying, no, you're not coming through here. And so there's a pushback. How much pushback is there? How can I determine that? Well, I know how much pushback because I would apply Ohm's law, V equals IR. There's a voltage drop. So I call the pushback, it's actually a voltage drop. This was a voltage push, but once it gets over to here, it's going to lose some of that push because the resistor is pushing back the opposite way. But the same equation we've been applying all along applies right here. If I know the current through this circuit, I can calculate the voltage pushback or the voltage drop across this resistor by using Ohm's law. So what is it going to be? Well, it would simply be the current that goes through that resistor, which in this simple circuit is 6 ohms. 6 ohms. I don't know what that current is right there because I have to calculate it. It would be whatever the current is here. Let's just calculate it real quick. V equals IR. If my V is 1.5 volts, and my resistor is 2 ohms, and my current through the whole thing is 0.75 amps. Okay, got that? So in this simple circuit, I have 0.75 amps flowing through the circuit. Okay. Now, you're going to think this sounds kind of ridiculous because it's so simple, it seems kind of ridiculous, but it really is that simple. What's the voltage drop across this resistor? Well, it makes sense. It's the only resistor in the circuit. So the voltage drop against this one resistor is going to exactly equal the voltage push over here. How do I know? Let's double check. V equals IR. I now know the I because I calculated it. It's 0.75 and the resistance was 2. I'm right back to 1.5 volts. So the voltage drop across this resistor is 1.5 volts. So the AA battery pushes this way with 1.5 volt, pushing current, and this one resistor pushes back with exactly the same amount. So by the time I get back over across here, I have 0 voltage. I have no more push. Now what if I added multiple resistors in there? Let's put a second resistor of 2 ohms. And let's do some quick calculations. Through this circuit, what would my current be? Well, V equals IR. Voltage, I'm going to rearrange. V divided by R. What is my voltage? It's 1.5 volts. What is my resistance? Remember, I have 2 resistors now, so I have to add them. 4 ohms. So what am I going to have? It's half. I should be able to do this in my head, right? 0.375 amps. So the total current through this circuit is 0.375 amps. But now you may ask, what is the voltage drop across each of these resistors? Well, I know that the sum of these two have to equal the 1.5. I can do this in my head because the 2 resistances are exactly equal. So if the total voltage across all of these resistors has to equal 1.5, then the voltage drop across each of these must be 0.75. So I have 1.5 voltage push, I have 0.75 volts resistance, pushback against this resistor, and another 0.75 volts pushback across that resistor. So the total voltage drop across these two equals the total voltage applied. The sums of the voltages all have to equal 0. That's the second of Kirchhoff's law. If I scan around this whole thing in a loop, all the voltages have to equal 0. So let's try that. I start over here. I'm going to check all the sums of my voltage. Okay? So, eeks. Better? Sum of my voltages. I start right here. I have a positive 1.5 volts. Come around here. Remember, this is a voltage drop, and we calculated that was 0.75. So I subtract 0.75, and then I subtract another 0.75, what do I have? This all equals 0. And that's what Kirchhoff's second law says. If you scan around in a circle, the sum of all the voltages must equal to 0. The source is always positive. Resistors and things like that in the circuit are always negative. They're subtracting from the voltage, and this is adding to it. So I want to walk you through this current up here. We're going to talk about this one and kind of break it down a little bit. It's kind of hard to see in the book, so I'm going to redraw on the whiteboard, and then I'm going to walk you through doing the calculations for this one. Okay, I'm back. I wanted to draw this one without you having to watch. All right, so we're going to go through and we're going to apply Kirchhoff's second law, saying that the sum of the voltages must equal 0 for each loop. Now, there's actually multiple loops here that you can look at. So let's start with this simple one. There is basically, if I ignore everything, let's start with that. There. We're going to start with this simple portion of the circuit right here. There's essentially a loop that goes around this way with just one resistor in there. Now, in this particular one, they have just labeled it V1. And he wants us to find what would the voltage drop be at V1. For each circuit, each loop, all the voltages have to equal 0. Well, I don't even need to write this out. I can just look at it very quickly and say, well, the voltage drop across this first resistor must be 8 volts. Because if it's going to add up to 0, here's positive 8, and then I must have subtracting 8 to get back to 0. So I can replace V1 right here with 8 volts. Now let's move on and do a second loop. Now there's several, but you can look at each one individually. I'll draw the loop in red like he did in the book. So we're going to do a loop around this one. And we're going to ignore, okay, don't pay any attention to my notes on the other side. That's from a previous class. So we're going to look at this circuit now. I actually only have one unknown in here. I have 8 volts, 4 volts, 2 volts, an unknown voltage labeled V2, and 1 volt. Remember, the sum has got to equal to 0. So what do I have across here? Now it's a little bit confusing because you think, well, this was a voltage drop over here, right? But actually what I'm going to do is I'm going to look at it more from okay, I need to back up a little bit. One thing that I wasn't drawing on here that might make it a little confusing is as we were going through this particular loop, I should have drawn on here the positive and negative, right? So as we were going through this loop, this was my voltage source, so the voltage drop across this one would be just the opposite, right? It'd be coming in with a positive voltage and coming out with a negative voltage. Okay, so I should have labeled that. Now let's come over here and look at it this way. All right, so now let's go through this loop. So I'm going to start at, let's say I start at this point right here. You just need to pick a point. So I'm going to pick a point and I'm going to go around. Now I know the voltage drop across this is going to be, it's going to be a voltage drop. I'm going to go from a positive to a negative, right? So let's add it. So if it's a voltage drop, that means it would be a -4. So I have a -4. I have another voltage drop. I'm going from positive to negative, so that's another -2. I'm also having another voltage drop, so I'll subtract V2, come back over here, another voltage drop going from positive to negative, so -1. But now look what happens. I get over to this one, and now look at the polarity on this one appears to be reversed. I'm going from minus to positive, so it's actually going to be +8. So add all these, and it has to all equal to 0, right? So I'm going to bring V2 over here, do my simple algebra, and what do I have left on the left side? I have -4, -2, -1, and +8. So that's -7. -7 plus 8 leaves me with a -1. So V2 equals -1. +1. You knew that. I was just checking to see if you were paying attention. So V2 I can replace with 1 volt. So now I know the voltage drop I get across that resistor. Now let's go see what V3 is. So let's move over to here. Let me erase this down here. Let's move over to this one. What's the voltage drop across V3? So I'm going to do this loop right here. And I'll just pick this as my arbitrary starting point to start my loop. So I know this is a voltage drop, so I'm going to go from positive to negative. If it's a voltage drop, I have to label it as minus V3. Come around here. Now I'm going from negative to positive, so that's going to be plus 1 volt, negative to positive, plus 2 volts. It has to all equal to 0 according to Kirchhoff's law. Bring V3 to the right, and what's left on that side is 3. So I can now replace that with 3. So now that was an application of Kirchhoff's second law, that across any loop the voltages must all equal 0. Okay, if you have a chance, make sure you study his analogy right here, the steps. I think this is a pretty good analogy to help you understand. If you climb a certain number of stairs up to get to a certain floor, you have to climb those same number of steps to get back down to the ground floor before you can start going up again. That's a pretty good analogy to use for your voltage drop. So now we're going to move on and start calculating, well actually we've been doing this already, some circuits. So I'm not going to do this example because we've actually done this a couple of times where you have a voltage and 2 resistors. We've done something like that. So let's move on to a more complicated one. How about if we do, this one's not too complicated, but we'll do this one, 11.10. So pause for a second while I draw it. Okay, we are going to move on to another problem. Specifically, we are going to do this one right here in the book, example 11.10. They want us to calculate the current, overall current through the circuit, as well as the current through each of these branches. They want us to find the voltage drop across each of these resistors, and then I think they want us to find the power in each of the resistors as well. So let's get started on that. So first step, I could just ignore that side and combine these 2 resistors into an equivalent resistance, right? Use Ohm's law and find the current. There's actually an easier way. So we're going to start by doing the easier way. We're going to start by evaluating, using one of Kirchhoff's laws, and evaluating the voltage across this loop. Okay? So if I come across this loop, according to Kirchhoff's law, the sum of all the voltages have to equal 0. So here I have a voltage source, and I only have 1 resistor, so I don't even have to write anything down. I know if I have 5.4 volts positive, then I must have 5.4 volts negative right here for the sum of them to equal 0. So I can go ahead and replace this with 5.4 volts. Let's do the same on this side. Let's see if I can go ahead and get the voltage across this resistor. What is V2? Again, the sum of the voltages have to add up to 0. Well, it's pretty easy because this particular loop, if I'm doing this loop around here, I only have 2 resistors. So I only have 2 things. I have a voltage positive 5 volts that we just calculated, so that one's got to be a negative. Got to go from positive to negative. So I can go ahead and replace V2 with 5.4 volts. So I know that the voltage drop across each of these is the same. Now let's pause for a second and talk about that, because so I have 2 resistors in parallel. It's actually, you can see now that each parallel branch is going to be exactly equal to the voltage source that I place across it. And it wouldn't matter how many resistors are crossed here, this whole branch from here to here is going to have exactly the same voltage as my voltage source right here. And likewise then the second branch from here back to that node is going to have a total combined voltage drop of 5.4. That's the way it works with parallel branches. Alright, so we got the voltages. Now can we find the currents? I actually, right here on this branch, I now know the voltage and I know the resistance So I have everything I need to find that current in this branch right here from node to node. I just use Ohm's law. I'm going to solve for I2. So I2 equals V over R, which is 5.4 volts divided by 14,000 ohms. And that ends up equaling 0.3, I'm looking in the book, 0.3857 milliamps. Or, if you didn't want to write out milli, that would be that many amps. But write milliamps, it's much neater. So I now know I2. What about I3? I can do the same for I3. It's going to be the same voltage, because we just calculated that up here, 5.4 volts divided by, this time a different resistance, 27,000 ohms, and it's going to equal 0.2 milliamps. That was a nice neat number, or that many amps, but write it like that. Okay, so we have the currents. So we have the voltages, and we have current I2 and I3. What about I1? Well, remember from Kirchhoff's law, at each node, the current coming into that node has got to equal the sum of the branches. It just makes sense, right? If you have so many electrons marching this way and they divide, then I know that these two have to equal the sum. So I1 is simply going to be the sum of these two. So it's going to be 0.3857 milliamps plus 0.2 milliamps. So that's 0.5857 milliamps. So now we can go back and find the powers. They wanted us to find the power across each of these resistors. I'm running out of room here. Let's slide the whiteboard this way. Oh, I can't really do that. Alright, I'll just slide over here. Alright, so we're going to come over here to calculate power. Now if you come back to, I'll go all the way back to the beginning of the chapter. The two formulas you need to memorize. One is Ohm's law, the other is the formula for power. P equals VI. So that's what we're going to apply here. So let's look first across this resistor. Power is going to equal the voltage times the current. The voltage is 5.4 volts. And the current we just calculated for this one right here, I2, was this, 0.3857 milliamps. Or I'll put it in terms of amps. Because power, I need to be voltage times amps. Okay, so what do I end up with here? I get 2.0827 times 10 to the negative 2 watts, because that's the unit of power. Voltage times current equals watts. But I'd really rather not leave it written with a negative exponent there, so I could write it as, but that's a lot of zeros. So how about if I just divide it by 1,000 and write it in terms of milliwatts? Remember, milli is 1,000th, 1,000th of a watt. So I'm going to divide by 1,000. So it's basically going to be 2.0827 milliwatts. Now I can do the same to find the current across the other resistor, but you get the hang of it, so we will stop there. Okay, so now I'm going to walk through example 11.12 on page 260. They want us to find the currents through each of these loops as well as the power across each of the resistors. So let's begin looking at this. Now the interesting thing is the equivalent resistances for this particular example were calculated in a previous example, but let's just go through it again for practice. So first thing I would like to do is see if I could figure out the voltage drop across each of these resistors. So if I look at this loop, I can't really do that yet, can I? Because I have two separate values. I can't find the voltage drop across each of those unless I know the current or the equivalent resistance. So I could find the equivalent resistance of those two, so let's do that. They are in series, so I would simply add them. So this right branch could be redrawn simply as one resistor, and the value is going to be 10,700 plus 870. Okay, so that resistor is 11,570 ohms. So my circuit now looks like this. Oops, forgot that one there, didn't I? Can I calculate the voltage now? Well, I don't know the voltage across this resistor. And so I really sort of need to, can I come around here and apply Kirchhoff's law and look at the voltage across that loop? No, not quite yet. I need to find some other equivalent resistances. So let's keep going. What I can do now is I can combine these two they're in parallel, so I can combine them into one equivalent. So again, to do that, you would use that formula. And I'm not going to actually write out the answer because we've done that several times. So I'll just show you, you would plug in R1 and R2, and then you would add them down here. Okay, so when I combine all those together, I guess I am doing it. What do I get? I did that wrong. Let's try again. 7,600 times 11,570 divided by 7,600 plus 11,570. I think this is one of the ones we went through earlier. Okay, so I end up with 4,586, so I can draw all this down now to basically one resistor that equals that value. Okay, can I find the voltage drop now? I'm close, but I still have two resistors, and I don't know the current. So I sort of need to combine these two back down into one. And how would I do that? I would simply add them. So my equivalent, again, is going to be, well, I'll just add it here. It's going to be this one plus this one. Okay, so now I can draw this all the way down. So that circuit breaks down into equivalent imaginary circuit that looks like this. And this is the equivalent resistance. So I can find the current now through here. And that means once I know this current, I can back up and find many other things. So what is I1 going to equal? V equals IR. Now it's possible in the book he took a slightly different path. There's several different ways you could approach this because we're doing in lots of little steps. You could do it as step A, B, and C, or B, C, and A, and oftentimes you'll end up in exactly the same place. I mean, if you do it correct, you should end up in exactly the same place. So I may not be doing the same steps in the same order that he is, but hopefully my values will be the same. Okay, so I'm solving for current. So I have V over R. voltage divided by my current, resistance, I mean, not current, to solve for current. So I have 9 divided by 7886.96. So for my current, I have 1.14112 e to the minus 3. I'm just going to divide that by 3 and call it milliamps for now. So I have 1.14112 milliamps running off the page. Can you see that? There we go. So this is my equivalent circuit. So I can now come up here on my original circuit and I can draw in, I know that the current here is 1.14112 milliamps. Okay, so let's keep moving along. I'm going to erase this now. So I did all that in order to be able to find the current through here. So I can actually, now that I know the current that goes through this first loop right here, can I find the voltage drop across each of these resistors? I actually can, because I know the current through here. I don't know the current through this one yet, but by applying one of Kirchhoff's laws, I can figure it out. So let's start. I know that the sum of the voltages has got to equal 0. So let's start here and work our way around. So first of all, I have positive 9 volts, because I'm going from negative to positive, so I have positive 9 volts, and then I'm going to have a voltage drop across here. I'm going to go from positive to negative. What is that voltage drop? Well, it's going to equal, I'm going to use Ohm's law to figure that out. It's going to equal current times resistance. So, and it's going to be a drop. So current is what? 1.14112 times 10 to the negative 3. I'm working in amps here. Times the resistance, which is 3300 ohms, because it was kilo. I multiplied by 1,000. So that's the current drop across that resistor. Now I get to this one. I don't know what the voltage drop across here is. Can I use V equals IR? Well, I can't really, because I know R, but I don't know the current here. Remember, I know the current coming into it. That's the 1.14, but it branches. And I haven't solved for how much is going down each branch yet. Haven't gotten there yet. But I'm just going to call this V1, and I'm going to solve for it, because I actually have, it's the only variable I have left. I can solve for it. Since I know they all have to equal 0, now I can solve, and V1 is going to equal 9 minus this. So 9 minus 1.14112 e to the negative 3 times 3300. Okay, so now you're probably asking, how come I'm writing out all these decimal points? I'm not obeying significant digits, and I take points off in your test if you don't obey significant digits, blah, blah, blah. I can just hear you thinking that. In this case, we have to carry it all out because we have so many interim calculations that if you're rounding at each of these steps, you're going to lose so much. By the time you get your final answer, it's going to be grossly inaccurate. So yes, we don't obey the significant digit rules here. When you're doing all these interim calculations, carry lots of digits out. Now, do you need to carry 10? Probably not, but 4, 5, 6, those are all fine. So I now know the voltage drop across this resistor. But aha, I'm starting to kind of eat this elephant one bite at a time. If I know the voltage drop across this resistor and I know the resistance value, can I not find the current? The answer is yes. So let's look for that. I'm going to rearrange that formula, I equals V over R. I know the voltage drop because I just calculated it. And I know the resistance because it's right there, that was given to me. So now I can find the current through this branch. It's going to be what we had earlier, divided by 7,600, which I get amps. Okay, pretty small number, but I can put that in milliamps and I will have 0.688711 milliamps. A little over half is coming down this branch as opposed to that branch. Now that should make sense to you, because if you look here, there was a whole lot more resistance on this branch. 10,700 ohms plus about another 870, so over 11,000 ohms this way, whereas 7,600 or 7,000 ohms this way. So the resistance coming down this path is more than this. So obviously more of them are going to choose to take this branch than this branch, and that's what we saw. So we now know the current right here. So let's go ahead and fill that in. That is 0.6887 milliamps. Ooh, that's kind of small. Working our way down. What's the next step we're going to do? We now know the current, total current, we know the voltage drop, we know the current and voltage drop here, so now we need to finish this one. Can we do that? Well, remember Kirchhoff's law. The current coming into a node has got to equal the sum of the currents coming out of the node. I now know the current coming in, we said it's 1.14, and we just solved for this one coming out. We said it's 0.6887, all these are milliamps, so obviously I can find I3. It's going to simply be 1.14 minus 0.688 milliamps. So, okay, those of you that have this kind of calculator, I'm going to show you a trick on here and how to use this. So I'm going to calculate this current, but I've already calculated, oh, you can't really see very well in here. I've already calculated a lot of these currents. Can you see this? Ooh, there we go. All right, let's see if I can show you how to do this. All right, I already calculated the one current. If I use this button right here, I can go up to where I calculated the first current, hit the enter button right there, and it brings it down. Okay, and I'm going to subtract the second current, which I already calculated also. It is right there actually. So I use that button to go up, pick it, hit enter, it brings it down. So now look at what's down here. I have the first current minus the second current. So I didn't have to type everything all in again. I just hit enter and I get my new number. So that's a trick on how to use the TI-84. So I have 4.52409 times 10 to the negative fourth, or 0.452409 milliamps. Okay, so that's my I3. That is the current that's coming through this branch right here. Okay, so we're getting there, one bite at a time. What's left? Well, I pretty much know everything now, don't I? I know the current coming in, total current. I know the current down this branch. I know the current down this branch. I know all the resistors. I know everything now. Now, if I want to find the power dissipated by any one of these resistors, I just simply use this equation. So we'll just pick one, for example. Let's suppose I want to know the power across this resistor. Oh, I need to know the voltage, don't I? I don't know the voltage yet, do I? Actually, I can find the voltage drop across this one by using V equals IR, right? I don't have to do the whole Kirchhoff's law circle again because I know the current through it and I know the resistance through it, so I can find the voltage drop across it. So I already know everything there. So let's find the voltage drop. Or we could do something else. If we know the equation for power is V equals IR, and we know that P equals VI and V equals IR. What if I combine them? What if I take this equation right here and stick it in right there? What do I have? This is just another form of that equation up there. We could do it in 2 steps, which is actually what they usually do in the example in the book. They have you go through and calculate the voltage first, and then you stick the voltage into here, multiply by the current to find the power. So you could do that in 2 separate steps, or you could combine them into one this way. I'm going to do this. So what's the current through this resistor? It's this 0.452409 times 10 cubed. Why? Because it's milliamps. So that's how many amps I have, times resistance, 870 ohms. Multiply it out. I'm not going to do that. I'm lazy. And you'll get the number of watts. So that's all there is to it. So we have walked our way through a very complicated circuit.